Now I want to create a graph out of this whole thing. As an example, n equals 4, let's take m equals 3, and my graph is C1 is the clause, let's take x1 or x2 or x3 bar, C2 is going to be x1 bar or x2 or x4, and C3, let's take it to be x2 or x3 or x4 bar. Okay, so from this formula I need to produce a graph. How do I produce this graph? Well, here is the idea. Okay, so the graph is going to have 3 layers. Okay, so I'm going to create, for every clause, I'm going to take the literals in the clause and make vertices out of them. So here I will have x1, x2, x3 bar for the first clause. For the second clause, I'm going to have x1 bar, I'm going to have x2, I'm going to have x4. The third clause, I'm going to have x2, I'm going to have x3, and I'm going to have x4 bar. So if I have m clauses, I have 3m vertices. Okay, and then the second part is I'm going to connect from between some clause ci and cj. I'm going to make all possible connections, except that I will never connect a vertex to its negation. Such a connection is not allowed, number one, and I'm not going to add connections between vertices in the same clause. So vertices in the same clause x, let me call that literals that belong to the same clause, li1, li2, I will not connect them. So I'm never going to connect literals in the same clause. I'm never going to connect x1 to x1 bar, right? So I'm not going to make those connections. I'm not going to make this connection. I'm not going to make this connection, but I'm going to make all other connections. Okay, so there's going to be a lot of connections, too many to show here. I will not show all of them, but hopefully you get this idea of all the connections. How many edges? At most 9m squared edges, because there are m clauses. So between every pair there's going to be m squared at most, and then there's going to be 9 between two of these pairs. So 9m squared and 3m. So this can all be done in polynomial time. In fact, with n variables and m clauses, you can do it in theta n plus m squared time. Very good. Okay, so this is the graph. And now I claim that if there is a clique of size m being the same as the number of clauses, if and only if the original formula is satisfiable. So let me show how this works. So if there is a clique of size m, such a clique can select exactly one vertex from every clause. So from every clause, such a clique can select exactly one. Why is that? First of all, it cannot select more than one. If it selects more than one, let's say it selects 2 here, but there is no connection inside between two nodes in the same clique. There is no connection between two nodes in the same clause. There is no connection, and therefore, if I manage to find a clique which is the same size as the number of clauses, well, I have to choose exactly one vertex from every clause, corresponding to every clause. Let me go ahead and assign this vertex the truth valuation true. So in this case, I would assign x1 to true, x2 to true, and let's say x4 bar to true. Well, that means that I will assign x4 to false. You get the idea. So this is the truth assignment that I derived. This truth assignment cannot be contradictory. Cannot be contradictory. By that I mean I should not be able to assign xi to true on one side and xi bar to true in another place. I should not be able to assign xi to true and xi bar to true. And that will never happen, because if I assign xi to true and xi bar to true, which means that they are part of the same clique, which means that I must have connected xi to xi bar. but that is not possible. I never add connections from a variable to negation, so this will never happen. Okay, so what do I have? If I have a M clique, then that clique must have selected exactly one. So here, for example, I have a M clique involves x1, x2, and x3. This clique must have selected exactly one vertex from every clause, and each of these vertices must be connected to every other vertex because it's a clique. So therefore, if I took the corresponding truth assignment, which is assign the variables that are selected in the clique to true, that gives me a truth assignment. And by the way, this truth assignment must satisfy the formula, because in every clause, at least one of the literals has been assigned true. And if one of the literals has been assigned true, which means that the clause is satisfied. And if every clause is satisfied, then C1 and C2 and Cm must be true. So if I find a clique of size m equal to the number of clauses, then I find that the original formula is satisfiable. And by the way, if the original formula is satisfiable, then I should be able to find a clique by knowing the truth assignment to that formula, because I can take any truth assignment and make it into a clique. Okay, and therefore 3CNF SAT can be reduced in polynomial time to K clique such that the answer for K clique, yes or no answer, is exactly the yes or no answer to 3CNF SAT. And if you understood this, you have understood your first NP completeness reduction. Start from a problem that you know is NP complete and reduce to the problem that you wish to prove. Never get this direction wrong. And this shows that if I can solve K clique in polynomial time, then I can solve 3CNF SAT in polynomial time, and therefore K clique is NP complete. Another way of looking at it, everything is already known to be reducible to 3CNF SAT, and if 3CNF SAT itself is known to be reducible to K clique, then of course by composing these reductions, everything is known to be reducible to K clique. Okay, and hopefully now you can see how the game is played. Alright, so in the next lecture, I'm going to show you a few more NP completeness reductions, and these are always going to be somewhat tricky. It's going to take some work to make these reductions happen, but now that we are off and running, we can start to get some ideas on how these reductions can be done. Alright, see you in the next lecture. Bye. Okay, so in this lecture, we are going to give you a brief introduction to some very interesting and important NP-complete problems and talk about how we can prove that they are NP-complete in cases where these proofs are easy and many of these proofs are classic proofs, so we'll talk a little bit about those. So we looked previously at the Cook-Levin theorem without a proof, and we claimed that the 3CNF SAT problem is NP complete. And without going into the 3CNF SAT problem, we know that it's a AND of clauses. Each clause is an OR of 3 literals. A literal can be a variable or the negation of a variable. Okay, so we saw all of this. Now, there are many variants of SAT that are interesting. All right. So some of these variants can be polynomial. So as an example, if you consider 2CNF SAT, where every clause Ci has just 2 literals, so you are only allowed 2 literals per clause, you can actually prove that this can be solved in polynomial time. On the other hand, with 3CNF SAT, the best known algorithm, and by the way, the algorithm runs in about theta n squared, where n is the number of variables in the problem. With 3CNF SAT, you have an entirely different story. The best known algorithm takes about 2 to the power n, where n is the number of variables in the problem. And this is an entirely different order of magnitude. So just going from allowing clauses with just 2 literals to having clauses with 3 literals increases the problem complexity a lot, or at least seems to increase, and we don't know if 3CNF SAT can be solved more efficiently. We just don't know. All right. Now, what about greater than 3 CNF SAT? What if you have literals with more than 3? So let's look at a literal, let's say, for example, let's look at a clause with 6 literals, x1, x2, x3, x4, you can have a bar if you wish, x5, x6. Now, the interesting thing is there is a trick that allows me to split this into multiple literals with 3 variables. I could do x1 or x2, or let's add a fresh variable. Let's call it z, and not of z or x3 or z1. Okay, so z1 is going to be, these are going to be continuation variables, right? So, and then you can have and not of z1 or x4 bar or z2, and not of z2 or x5 or z3, and not of z3 or x6, let's say. So now you can split this entire clause into a bunch of clauses with fresh variables that do not previously exist in the problem. So add fresh variables and you can split a clause with, let's say, 6 literals into multiple clauses with 3. And by the way, the last clause you can just repeat x6 if you will. So if you have greater than 3 CNF SAT, you can reduce it to 3 CNF SAT. So it's the same as 3 CNF SAT. So you can make a simple reduction to 3 CNF SAT. Okay. On the other hand, 3 CNF SAT is an order of magnitude more complicated than 2 CNF SAT. Now, of course, there are some variations of SAT that are also in polynomial time. One very popular variation is called Horn SAT. Okay. So in Horn SAT, each of the clauses has the following form. So it's a special form of SAT where each clause has the following form. And the literals are all but one of the literals in the clause are going to be negated, except one literal is going to be appearing in the positive form without the negation. So for example, you can have x1 bar or x2 bar or x3, x1 bar or x3 bar or x5, x2 bar or x4 or x6 bar. So these kind of clauses are called Horn clauses. And if you only have Horn clauses in your problem, then Horn SAT can be solved in polynomial time. And furthermore, this is a very important, this led to a very important development. It led to a form of programming. So it led to the development of a programming style, something called logic programming, okay, which is not so popular these days, but it's still used in many contexts. It's called logic programming. If you have heard of languages like Prolog, they were based on this idea of Horn clauses, okay, and the algorithm for solving Horn SAT forms the basis of these programming languages like Prolog. For example, in the modern version, there is something called Datalog and so on. Okay, so this is a very powerful idea, and this is an example of a variant of SAT that's actually polynomial time. Okay, so there are many variants of SAT. Okay, and let me explain one more interesting variant of SAT, and this is called max SAT. Okay, so in the satisfiability problem, you are given clauses C1, C2, and Cm, and your goal is to find a truth assignment to satisfy all clauses. Okay, but what if I just want to satisfy k out of m clauses, or at least k out of m clauses? So I don't want to satisfy all of them. I just want to satisfy at least k out of m. Okay, and this problem is called k max SAT. What is that? you're given a SAT formula, let's say a CNF, 3CNF SAT formula, and you're given a number k, yes, if there is a truth assignment, that satisfies k out of m clauses, at least k out of m. It can satisfy more, okay? Okay, no otherwise. This is clauses. Okay, no otherwise. All right. So this is an example of K-max SAT, and in fact, you can easily prove that K-max SAT is NP complete by reduction from the 3CNF SAT problem to K-max SAT. Okay, it's a nice exercise to do so. Very, very nice exercise to do so. Okay. Plenty of problems involving graphs that are also NP complete. Okay. So for example, one very interesting problem we studied was the K-clique problem. Given a graph, is there a clique involving K nodes, and a clique being a subset of the graph where every node is connected to every other node. So in this example, this graph has a phi clique. Okay, so we saw this, and we saw from reduction to 3SAT to K clique. We saw that. Okay. Now there are other problems that are also NP complete. An example of this is a vertex cover problem. So what is a vertex cover of a graph? So suppose I have a graph with some vertices and some edges. Okay, so here is an example. A vertex cover is going to be a subset of vertices. So let me choose one vertex here, and let me choose one vertex here, such that for every edge in the graph, so for every edge in the graph, okay, so if you choose every edge in the graph, at least one of the endpoints of these edges is incident on the vertex cover. So here is the first vertex in the cover, second vertex in the cover, and if I take the set 1, 2, then you see every edge in the graph is either one of the endpoints is going to lie in the vertex cover. So vertex cover S is a subset of the vertices such that for all edges, okay, one of the endpoints, at least one of the endpoints of E lies in S. Okay, so it's a set of vertices that cover all the edges. So let's take another example. Here is another graph. What is a vertex cover for this graph? So I could choose vertex 1, right? Vertex 2, vertex 3, vertex 4, and that gives you a vertex cover with 4 vertices. Okay, and we are interested in this. Given a graph, we are often interested in the smallest vertex cover. But since the smallest vertex cover is not a decision problem, so we have the decision version of this problem is the K vertex cover problem, which is asking, is there a vertex cover with K or fewer vertices in the graph? Okay, now K vertex cover is in NP. Why is that? You can always figure out what the certificate should be. The certificate is going to be at least K at most K vertices, actually K or fewer vertices. Okay, this can be K, but it can even be fewer than K, right? Such that these vertices together form a cover. And how do we check if it forms a cover? Take every edge in the graph and check that one of the endpoints of the edges belongs to S. At least one of the endpoints must belong to S. Okay, and if we check that, then we are done. Okay, and that's an easy check. Okay, that's the amount of time this check takes is the size of the number of edges in the graph, because we are simply checking for the number of edges. All right, so this is linear time, and the certificate can be checked easy. So vertex cover is belongs to NP. So vertex cover is in NP. Okay, oh, sorry about that. Okay, is in NP. All right, so now we are left to prove that it's NP complete. How do we prove that vertex cover is NP complete? Well, there is an easy reduction from the K-clique problem, okay, which is a known NP complete problem. We just proved it, to vertex cover. So what's the idea? I have a graph G and I have a K. Okay, I'm going to convert it to a new graph G hat, a new number K hat, such that if I can find a vertex cover in G hat of size K hat, then I can find a clique in the original graph in G of size C. Okay, so of size K. So I need to transform G and K into G hat and K hat. Okay. And the idea is based on the following observation. So let us take an example of a graph. Okay, so here is a graph. Okay, and I need to know if there is a 3 clique in the graph. Okay, so here is what we do. Let us look at all the edges that are not present in the graph. Okay, so let us look at all the edges that are not present in the graph. Okay. So in red, I have drawn all the vertices not in the original graph. And so if you now take the original graph and just look at the edges that are not present, you get a new graph called the complement graph. So in the complement graph, I'm going to remove all the edges that are not present in the original graph. I'm going to consider only those edges that are not present in the original graph. So this is going to be the complement graph. Okay. Now here is the idea. If there is a K-clique in the original graph, then there is n minus k, where n being the number of nodes, vertex cover in the complement, and vice versa. Okay, let us try and prove this. So suppose I have a graph and I have k nodes in the original graph that are all connected to each other. So k clique in the original graph. Okay, so what's going to happen, and let's look at everything else in the original graph. Okay, let's look at everything else outside of this k clique. Okay, so suppose I had a k clique, and let's call this k clique C. So C is the set of vertices in the k clique. Okay, so then what happens is if I take the complement of this graph, then in the complement an edge is only present if it's not present in the original graph. So if I look at the complement, the set of these vertices that were originally part of this k clique, let's say these 4 vertices here, are not going to have any edges. Okay, so what is going to happen is the remaining, so every edge that is going to be present in the complement is going to involve, so if this is the set S, in the complement, the remaining vertices outside the set S, so V minus S, so everything outside the set S is going to be a vertex cover. So how many nodes are there? If there are n nodes total in the graph, if the clique is of size k, then n minus k size vertex cover, or less. Okay, it could be less. All right. So if there is a k clique in the original graph, then there is a n minus k vertex cover in the complement graph. In the complement graph, there's going to be n minus k vertex cover. And likewise, if there is a n minus k size vertex cover in the complement graph, then there is going to be a k click in the original graph. Okay? And because of this, what you can now show is that, okay, so because of this, and it goes vice versa, so what you can show is that there is a reduction from vertex cover. So there is a reduction from the clique problem to the vertex cover problem, and the reduction goes like this. Take the graph G and make its complement. So G hat is complement of G. And what is K hat? So K hat is n minus K. So if K is the size of the clique I'm looking for, now I'm looking for a vertex cover of size n minus K, and if I find it, then I know there is a K clique. If I cannot find it, I know there is no K clique. So this is a very, very simple reduction from K clique to vertex cover. And from this, I can prove that vertex cover is NP complete. Another example of a nice NP complete problem is called 0-1 integer linear programming. So in 0-1 integer linear programming, I am looking for, let's say, to maximize an objective function. Okay, so let's say it's like linear programming, but let's say 2x1 plus 3x2 minus x3, subject to some linear inequalities. Except that x1, x2, x3, the problem variables can only take on values in 0, 1. Instead of being real valued in a traditional linear programming, these are going to be 0 or 1, 0 or 1, 0 or 1. Okay. Now, because this is a maximization or an optimization problem, you can make a decision version to ask, is there a feasible solution? Feasible means it satisfies all the constraints in the problem, whose objective value is greater than or equal to some limit k. So you can always make it into a decision problem by putting some limit k. Okay. So interestingly, 0-1 ILP, integer linear programming, is NP complete. And the reduction is from 3 CNF SAT. Okay, and this would be a very nice problem that we will solve in our homework assignment. All right, it's a very, very nice reduction from 3 CNF SAT to 0-1 ILP. Okay. Now, there are many types of problems that are also NP complete. So, for example, we looked at knapsack problems. Okay, so we have a bunch of items, I1 through IK. Each item has weight W1 through WK. They have a value V1 through VK. We have a weight budget V. Can I choose which items to keep in my knapsack? So that I get value at least capital V. So this is the decision version of the problem. We saw this problem in dynamic programming, where we actually looked at the maximization version of the problem. Rather than saying, can I choose items to keep a value of at least V, we looked at how do I maximize the value. Okay, that was the optimization version. We are studying the decision version. All right, and there we found a pseudo polynomial algorithm. Right, so we found a pseudo polynomial algorithm which depended on W, and we had a discussion perhaps on why this was pseudo polynomial, why this dependence on W is actually exponential. This is very much like the RSA factoring algorithm, okay, where we got a theta square root n algorithm, but square root n is exponential because w is represented using log w bits in binary. So in terms of its bit representation, it's an exponential algorithm in dynamic programming. Is there a polynomial algorithm? It depends, because this problem is NP complete. So you can easily show that it's in NP, and you can also show it's NP complete. Okay, so it's one of the NP complete problems, and you can perform this reduction to problems like subset sum problem and so on. Okay, so there are very standard reductions. You'll find this in a lot of books. What are the others of NP complete problem? So traveling salesperson problem, which we saw. Given a graph with weights on edges, is there a way to visit all the vertices and come back where we start, so that the sum of the weights of the tour is less than equal to some budget W. So can I tour every vertex, come back where I start, under the sum of the weights being less than equal to the budget W? And this is another example of an NP complete problem. Okay, so, and this is a very, very important NP complete problem, something that people are very interested to know how to solve. And so there's a lot of investigation into problems like the traveling salesperson problem. Okay, and furthermore, there are tons and tons of NP complete problems. I already mentioned Resource by Gary and Johnson, which is a nice book. It's called Computers and Interactability. Okay, and it talks a lot about known NP complete problems from different areas. Okay, now with this I will conclude the whole discussion on NP complete problems. We will look at a few interesting proofs of NP completeness through some of the assignments, and hopefully the concepts involved behind NP completeness, the P versus NP problem, and the implications of various possibilities of P versus NP will be things that we will focus on in our assignments and trying to understand it further. So thank you, and I will see you in the next week. Bye. Okay, so in this series of lectures, I'm going to talk about quantum algorithms. Okay, and quantum algorithms are algorithms that are meant to be run on a very special kind of a computer called a quantum computer. And quantum computers are different from the kind of computers that we have running in our laptops or in our cell phones. These are computers that are based on the fundamental principles of quantum physics. And as such, quantum computing has made a lot of strides. People have taken quantum computers, which used to be very difficult to make, and now we are making larger and larger quantum computers. So the hope is that in the next 2 or 3 decades, quantum computing will start to become reality in some form. And therefore, it's worth studying quantum algorithms. These are algorithms that would run on the quantum computer to solve certain important tasks. So before we get into quantum computation and so on, the first thing I wanted to talk about is the relationship between computation and physics. Okay, so far in this course, we have been looking at algorithms. And our main view of algorithms has been to look at it from the point of view of implementation. So typically, if you take an algorithm, you would implement it in a programming language like Python. Now, Python is just a high-level programming language. Now, it gets interpreted and run ultimately in terms of machine instructions. And these machine instructions run on a CPU and memory. Okay, so this is the basic architecture of a computer. and because we are talking about quantum, we'll call this a classical computer. Okay, even though there's nothing classical about it, we'll still call it a classical computer, just like quantum physics is different from classical physics. All right, now if you dig deeper into this CPU, the CPU is made out of logic gates. Okay, so logic gates. Now if you dig deeper into these logic gates, those logic gates look like AND, OR, NOT. Okay, so these logic gates manipulate bits 1 and 0. Okay, so logic gates that manipulate ones and zeros. So ultimately computing manipulates ones and zeros. But what are ones and zeros? So typically 1 means a voltage level. Let's say I'm using it depends on some specifics. So let's say voltage level above 2 volts, and 0 means voltage level below 1.8 volts. Okay, so what we have done is we have mapped bits, zeros and ones, pieces of information, into physical states where we have mapped them into different voltage levels. Okay, and the same goes for memory. So if you look at memory, there are many types of memory. Okay, so in the olden days there used to be something called magnetic core, where we looked at magnetizing in different directions. So if you magnetized in one direction, that was considered to be a 1. A magnetization in the other direction was considered to be a 0. Likewise, in modern RAM, random access memory, you have a capacitor which stores charge. Okay, so store charge in a device called a capacitor. Okay, if you have taken some electronics, you know what a capacitor is, but these are not the kind of capacitors you get. These are capacitors that are built into a kind of a circuit called an integrated circuit. Okay, so here memory storage is basically done by changing the state of physical systems like magnetization, physical properties like magnetization or charge. Okay, all right. So overall, if you look at the state of computing, you go from the algorithms we learn in this class all the way down to electrons. Okay, so essentially when you're running something on your computer, it's basically a massive symphony or an arrangement of electrons that they move through different arrangements to do computation. So we are controlling the motion of electrons inside our integrated circuit, and that's what current is, that's what charge is. Okay, and once we are able to achieve that, we get computation. Okay, so it's the controlled motion of electrons, or the controlled symphony if you want to be more poetic. All right, so where does the difference between classical and quantum computing come in? So let's look at classical versus quantum physics very briefly. Okay, so classical physics is essentially the physics that came about because of the work of people like Newton and electromagnetism, Maxwell equations. Of course, Maxwell's equations were where the product of thought from many other people like Gauss and so on. But in any case, Ampere, Gauss, and so on. But in any case, this is the kind of physics where you have electrons, protons, neutrons, the particles that make up the matter, okay, and then you have light, which is not a particle, which is a wave, okay. So you have a distinction between electron, protons, and neutrons. And the other thing is everything exists in a continuum. So quantities like length, energy, momentum exist in a continuum. Exist in a continuum. What does that mean? Which means that you have zero length, and then you have all possible lengths between 0 and infinity. Likewise, you have zero energy, and you have all possible energies between 0 and so all energies are possible, all values of momenta are possible. So physical quantities like velocity, mass, energy, length, they exist in a continuum, okay. And sometimes this is called continuum physics. All right. And if you look at this kind of physics, it's not wrong. It's just the physics that we observe in the real world in macro scale. Okay, so this physics is enough to explain a lot of what we observe. It's behind a lot of things that we take for granted, like radios and televisions. Okay, at least radios. The old-fashioned vacuum tube radios, for example, could be built using this physics. Okay, I am not sure if the modern transistor radio can be built. That requires a little bit more sophistication. All right, but in the turn of the 1900s, at the turn of the 20th century, people started observing discrepancies. Okay. So people started observing discrepancies between what continuum physics predicted versus what what they were observing. Okay, and one example was the spectrum of elements like hydrogen. Okay, so the spectral lines. So when you take hydrogen atom and you heat it up, or you provide it some energy. So hydrogen atom has one proton and one electron. Okay, and when you give it some energy, it emits radiation back. And you can observe this radiation using a device called a spectroscope that results in a bunch of what are called spectral lines. Okay, and so every atom has its unique signature of spectral lines. All right, and so what classical physics should predict is that these spectral lines should have all possible energies from 0 to infinity. Okay, but what got observed was that certain lines where at certain wavelengths, you got radiation, and then you got no radiation at other wavelengths. So you got radiation at certain wavelengths, and this leads to spectral lines. And if you zoom in on these spectral lines, sometimes you have much finer structure, but you still don't get continuous emission. You just get emission at certain wavelengths. Okay. Another interesting phenomenon was what's called the photoelectric effect. So you have certain materials, certain metals, that when light falls on them, they allow electricity. So they conduct electricity, or they generate a voltage potential. So when light falls on the material, there is a voltage difference between the side on which light falls on and the side which is in the dark. Okay, and because of this voltage potential, you get electricity. But the interesting effect that people observed was that this depended on the frequency or the wavelength of the light. And so below certain wavelengths, so below light of certain wavelength, lambda, there was no photoelectric emission, and then photoelectric emission happened at certain wavelengths, and then beyond that, you got more and more wavelengths at which it happened. It's a complicated phenomenon, but there was a dependence on the frequency or the wavelength of light, which was unexpected. So all of this led to what is called the quantum hypothesis. The quantum hypothesis was that energy or light is emitted or absorbed in packets or quanta. Okay, so things like, so then light is also a particle in the sense of an electron, and this particle is called a photon. Okay, and likewise there is the reverse effect where things like electrons will behave like waves. Okay, and there is a classic experiment called the double slit experiment, where you make two tiny slits. Okay, you'd make two tiny slits and you pass a source of light. Okay, so this is called Young's double slit experiment. Okay, and you put a screen here, and what happens is at the center of the screen you have two light waves from the slit converging, and so you get a bright spot, let's say. But as you move away from the bright spot, you get what is called an interference pattern. So you get, if you look at the screen from this angle, so if you look at the screen, okay, from here, so you get your central bright spot, and then you get a series of rings of bright and dark spots. Okay, and this is called a diffraction pattern. Okay, and this happens because at various points you have light that's coming in from the couple, there is light coming in from two slits, and they interfere. Okay, so they interfere, and the interference can reinforce the two sources and give you a bright spot, or they can cancel away the two sources of light because the phase angles of the two sources are orthogonal or 90 degrees to each other. And when the phase angles are orthogonal, then the two sources will end up canceling themselves out. Okay, or 180 degrees they will cancel out. 90 degrees you would get half the intensity. So you get this diffraction pattern from the center moving out. All right, now the interesting thing is, if you ended up performing this with a source of electrons, okay, with a source of electrons and not too many electrons, let's say just with a source that's giving you like a few electrons at a time, you still get this interference part. You still, and instead of looking at a screen, if you have an electron detector, then what you see is the number of electrons detected still follows an interference pattern, which is not explained easily by quantum mechanics. By classical mechanics. Okay, and so what physicists almost in the case of Einstein they had to conclude rather reluctantly is that there is a duality in matter. So waves and particles are just interchangeable dual states of matter. So certain so there's a wave nature and there's a particle nature, and things like light, you see the wave nature more apparently than the particle nature, whereas things like electrons, you see the particle nature more apparently than the wave nature. Okay, so the more interesting thing is when you perform this double slit experiment. Okay, even more interesting is when you perform this double slit experiment and your source of light just emits a single photon at a time. So your light source is so weak that it's going to emit one photon at a time. or almost there, right? And then you have a detector here, or a screen, let's say. You may not be able to see it with the naked eye, but you can still detect it, okay? And the interesting thing is, even with a single photon, so that now the theory falls apart, because with a single photon, the single photon either has to go through one of these slits, so it can't go through both the slits at the same time, right? Because it's a single particle, it has to choose one of the two slits, okay? In that case, you should not get an interference pattern. If it goes through slit A, then it falls on the screen. If it goes through slit B, it falls on the screen. So you should not be getting an interference pattern. You should be getting a continuous distribution, assuming that this photon can be fired off in any angle at random, okay? You would get a continuous lighting up of the screen, okay? Over time, you will see that the intensity histogram is continuous, okay? Interestingly enough, this is not the case. What physicists observed is that even with a single photon, you get an interference pattern. But how is that even possible? Okay, so this is where things start to get a little bit weird. And by the way, one thing you can also do is you can put a detector here to tell me which of these slits did the photon go through. And the moment you put a detector here, the interference pattern vanishes. This is super interesting, right? So you get an interference pattern if you have no detector. So if you are unaware of, if you do not measure, let me be careful here, let me not tell you there is something extra sensory here. This is all perfectly explainable in quantum physics, all right? So if you don't measure what's happening, then you get an interference pattern even if there is a single photon at a time, okay? It's almost the photons interfering with itself. But if you make a measurement, if you actually put a detector here to tell you which slit did the photon go through, then the interference pattern vanishes, all right? Now how is that possible, right? So this is where quantum mechanics starts to get really interesting. And the idea here is this notion called uncertainty principle, okay? And this is really popular, and this is Heisenberg. And this is really popular. Lots of you might have heard it, even if you haven't taken a physics class in a long time. Now, what's Heisenberg's uncertainty principle? Well, Heisenberg's uncertainty principle is simply can be stated in many ways. So one way to state it, and this is how Heisenberg initially observed it, is when you measure something. So for example, if you measure the position of electron, okay, so if you have an electron and you want to know the xy position, well, the way to measure the position of something is to shine light on it, okay? But the problem is, when you shine light on it and you triangulate its position, that's going to move the electron away, so it's going to affect the velocity. The velocity is changed in an unpredictable manner, right? So you can no longer measure its velocity. And likewise, if you want to measure its velocity, what you will find out is that you can no longer measure its position accurately. Okay, so Heisenberg's uncertainty principle came with this realization that measurement changes the nature of the measured state ever so slightly, okay? And this, in the case of subatomic particles like electrons and protons and photons and so on, this kind of change of state can be fairly large and therefore fairly drastic, right? In the case of measuring the position of my cell phone, it's going to be a big macroscopic object, so shining some light on it is barely going to change it, right? It's going to be a feeble, teeny tiny amount of energy that's not going to affect it. But in the case of a photon, it does. Now, Heisenberg went one step further. Heisenberg and the physicists at that time went one step further. Not only did they say that you cannot measure something like position, velocity, they said at the deepest levels of matter, things like position and velocity are inherently uncertain. These are physical quantities. These are inherently random. Okay, in a very weird way, inherently random, which means that there is no definite position, there is no definite velocity, there is a distribution of possible positions, there's a distribution of possible velocities, and you don't get a single, you can't nail down. And likewise, if you go back to the double slit experiment, what happens here is you have the same photon has can be going through both the slits at the same time. The photon does not have a definite direction, may not have a definite direction in space. It may have all possible directions at the same time. So the same photon may end up going through both the slits and may end up interfering with itself. Okay, that's the best way we have to understand it, because our sensory experiences kind of fail us at that level. All right, that's number one. But the moment you put in a detector, okay, a detector, by the way, there's no such thing as passive measurement. To measure something, you are actively messing around with it in some manner. Okay, no matter how subtle, you are changing it in some manner. And the moment you put a detector, what happens is that this uncertainty collapses, and now because of the measurement, your photon either goes through A or goes through B. Okay, so what happens when you put a detector is that the uncertainty vanishes. You have subtly changed the experiment, and because of that, the interference pattern is no longer observable. Okay, so this leads to some very interesting idea that things can exist, and I'm going to use the word exist in a very loose, philosophically dangerous manner. Things can exist, and things is typically subatomic particles like protons, electrons, okay, photons, light, and so on, in multiple possible states at the same time. Okay, so for example, when you have electrons, electron has a property called spin. Okay, so electron can be spin up or spin down. Okay, and the spin of the electron, you can roughly understand it as it rotating around itself either in the clockwise or the anti-clockwise direction, but that is not a very good analogy, but that's enough for us. Okay, so electrons can exist as a spin up electron or a spin down electron, and you can measure this in terms of its magnetic effects. Okay, so electron spin, you can measure things in terms of but interestingly, quantum physics allows you to have an electron that can exist in this weird state, that's a spin up state or a spin down state, okay, at the same time. And whenever you measure the spin, it collapses. Okay, so because of measurement, you can think of it as collapsing to a definite state, like a definite spin up or definite spin down, and this is with half probability. If you repeat this experiment, half the times you would get spin up, half the times you would get spin down. Okay, there is the famous, if you go to the web, you can look up a very famous experiment or a thought experiment called the Schrodinger cat that exists in a state of living and being dead at the same time until you actually peer in and look. And when you peer in and look, what you will find out is that it will have definitely collapsed into either existing or having or being dead. And these are very interesting experiments like the Schrodinger cat experiment. And there is a lot of philosophy surrounding this. What is the nature of the world deep down? But we are not going to worry too much about this. All of this, we can distill this down into what we call quantum information. Okay, so in that, the basic entity, just like in classical information, the basic entity that we were manipulating were bits. In quantum information, we get what are called qubits. Okay, so just like bits can be 0 or 1, a qubit can be 0 or 1. Just like bits are mapped to physical states where voltage less than 2 volts, greater than 2 volts. So just like that, you can prepare qubits as manifestations of physical states like electrons spin up, electrons spin down. Okay, or you can manipulate the polarization of a photon. Okay, and you can create two different configurations. One of these configurations, let me call this, represent it as the 0 bit, and another configuration, let me represent it as 1 bit. Okay, and these are called pure states. Okay, and they are very much like classical states, 1 and 0. But what quantum mechanics allows you to do, it allows you to create what are called superpositions, which means you can have a qubit, and by the way, qubit is quantum bit, which can both be 0 and 1 at the same time in a quantum sense. And you would write something like this. Okay, and I'll make this more formal in the very next lecture. And in this, you can say this is a 0 or a 1. Okay, and this is a quantum state. Whereas these are called pure states. This is a quantum state or a superposition state. And if you make a measurement, this collapses, and with probability half, this becomes a 0, and with probability half, this becomes a 1. Okay, so these kinds of superpositions are going to be fundamental objects, or qubits are going to be fundamental objects which we manipulate in quantum mechanics or in quantum computation. Okay, and when we manipulate these qubits, we are able to have these things be in two different states, or have two different values at the same time. So which means that in quantum computation, we can exploit this to get us an unbelievably interesting level of parallelism. Okay, and we can exploit this parallelism in very interesting ways. And I will start working towards this in the very next lecture. See you then. Bye. Okay, so in this lecture, we'll talk about qubits and quantum operations. Okay, so we looked at qubits at the very end of the previous lecture, and we saw that in a quantum system, you can have states like 0 and 1. Okay, and these are called pure states. All right, and these could correspond to things like electron with spin up, and this could correspond to an electron with spin down, let's say. Or you could build up a photon with a particular direction in which it's polarized, and so on. All right, so they are mapped to physical states, but we tend to not worry too much about the mapping here, because we are interested in algorithms and not in building quantum computers, which is topic which is an advanced topic in physics and not quite in scope of what we are teaching. All right, but the interesting thing in quantum physics is these pure states can combine and form superpositions. As an example, you can have a superposition of state 0 and 1. Okay, and this is a superposition. It's a mixed state. It's a superposition state, and this kind of a state it's going to be either 0 if you measure it. It's going to be 0 with probability half. It's going to collapse to a 0, or it's going to collapse to a 1 with probability half. All right, so formally, a superposition is written as some linear combination alpha 1 plus alpha 2 times the state 1. So it's going to be a linear combination, and this 0 and 1 are vectors, but they are not vectors in a normal space. They are vectors in a special kind of a space called a Hilbert space. Okay. What's a Hilbert space? Hilbert space is an abstraction of your standard vector spaces with something called an inner product norm, and it's a complete inner product space. We'll not worry about that. Just these are some vectors. Okay, so these are some vectors that are describing the physical properties of spin up and spin down, let's say, and you can combine them with some linear combination. One thing about quantum mechanics is alpha 1 and alpha 2 are complex numbers. So as an example, you can have the state I times 0 plus 1. Okay, and this is an example of a superposition state. Okay, this is an example where I is square root of minus 1. It's an imaginary number. Okay, so these coefficients can be complex numbers. All right, so this is an example of a state. Now the modulus of the state is going to be the sum of the moduli of each of the individual elements. So this is a 1. So in this case it's 1 plus 1, which is 2. Okay, so very good. So in fact this should be which is 1 plus 1, 2, and so this is the square of the modulus. The modulus of the state itself is square root 2. Okay, so if you have alpha 1 times 0 plus alpha 2 times 1, its modulus is nothing but the modulus of alpha 1 squared, okay, plus the modulus of alpha 2 squared, okay, and the square root of the whole thing. All right, so for example, the state 0 plus 1, its modulus is 1 squared plus 1 squared, square root of that, which is square root of 2. So a quantum state, we will try to normalize it to have modulus equals 1. So instead of having the state 0 plus 1, I will add a normalization constant to make the modulus 1. So for example, you could have the quantum state half of 0 plus 1, and you will need to put a normalizing constant which is half squared plus 1 squared square root, okay, and that's square root of 3 over, so 1 plus 1 over 4 is 5 over 4, so square root of 5 over 4, that's square root 5 over 2. So I will divide by this modulus, so I'll get 1 by square root 5 of 0 plus 2 by square root 5 of 1. So this is going to be the normalized state, and I'll always keep it normalized, and this is going to yield upon measurement, it's going to yield the state 0 with probability 1 over 5, and it's going to yield the state 1 with probability 4 over 5. So upon measurement, things collapse and stay collapsed. So what's the basic idea in quantum computing? So the basic idea in quantum computing is to prepare some qubits, and run some operations on qubits, and these are going to be quantum operations. Okay, and they are very special. I'll talk about this in a second, and then do a measurement, and you get an answer. Okay, so this is going to be the way a quantum algorithm will run. All right, so far we've looked at single qubits. single qubits. Now you can look at multiple qubits. And something very interesting happens, right? So for example, you can have bit 1, which can be, let's say, in a quantum state. Okay, so this is bit 1. Bit 2 can be in a quantum state. Okay, now what's the difference between having a plus here and having a minus? Well, that affects the phase. Okay, so quantum states have amplitude and a phase, so this affects the phase. The amplitude is 1, the phase is going to be affected by having a plus 1 or a minus 1. Okay, now interestingly enough, you can view them in a plane. So if you have one bit, you can view these. So for example, bit 1 is going to look like a vector like this. It's going to make a 45-degree angle. All right, and this is a B1. B2 is going to look like this. This is B2, and it's also going to make a 45-degree angle with the 0. All right, so you can think of these as not just zeros and ones, but now they have a direction or an orientation in space. All right, and that's going to be exploited by the algorithms. All right, so it's going to be something we'll exploit later. All right, very good. So you have multiple qubits. So in a multiple qubit system, so you can have the bits B1 and B2. So as an example, let's take 2 qubits. Let's say C1, or yeah, let's call the first bit C1. Let's say that's in the pure state 0, and C2 is in the pure state 1. Then combining these, you can write it down as a pure state 0, 1. And this is just the notation we use in quantum computing. This is the value of bit 1. This is the value of bit 2. Okay, and now you can have superposition. For example, you can have 0, 0 plus 0, 1. Sorry, 0, 0, in this case minus 0, 1 plus 1, 0 minus 1, 1. Okay, and to normalize this, what do I have to do? I have to divide this by 1 by 2. All right, and so this is an example which is just the bit B1 and B2 together. Is this all right? And this way of tacking two systems together has a name. I won't go deeper into this, but if you're interested, this has a name. This is called the Kronecker product. So you take B1 and B2 and you make the Kronecker product, which is simply saying make a single system that has 2 bits B1 and B2. Okay, and you get this system. Now this system is, you can interpret it upon measurement. What does it give you? With 1/4 probability, it gives you 0, 0. With 1/4 probability, it gives you 0, 1, 1, 0. With 1/4 probability, and with 1/4 probability, it gives you 1, 1. All right, very good. So in general, if you have a quantum system, you have alpha 1, 1. It can be in state 1, plus alpha 2, it can be in state 2, plus alpha n, it can be in state n. Okay, and these states can be multiple qubits. All right, now when you measure the system, and by the way, the modulus of alpha, the summation of the moduli squared must be equal to 1. Okay, so summation of the moduli squared must be equal to 1. So then with alpha 1 squared probability, the moduli of alpha 1 squared probability, it becomes S1. With summation moduli alpha 2 squared probability, it becomes S2. And with alpha n squared probability, it becomes Sn. Okay, so it collapses to one of these pure states, let's say, upon a full measurement. All right, so this is very, very important. Okay, so now if I take a state like, for example, what does this do? Upon measurement, this state with probability half gives me 0, 0. With probability half gives me 1, 1. So this is a 2 qubit state. Let's call this Q1. Let's call this bit Q2. Interestingly, what happens is I have two bits, Q1 and Q2, okay, and I have made this system where if I measure, and it depends on which one I measure. I can measure Q1 or I can measure Q2 or I can measure both at the same time. Let's say I measure Q1. Even if I measure Q1, okay, if I measure Q1, what happens? If I measure Q1, this state, I will get with half probability Q1 equals 0, with half probability Q1 equals 1. This is Q1, Q2. But interestingly enough, this system also does the following. Whenever I measure Q1, Q2 also collapses. Immediately, you imply that Q2 is 0 and you imply that Q2 is 1 in this case. So when I measure Q1 or I measure Q2, if I measure one of these two bits, the other bit collapses as well. Okay, and the state that has this property is called an entangled state. Okay, so let us look at what is an example of a non-entangled state. We've already seen one before, and that comes from the previous example here. So let's write down this example. So that state was basically up to a normalizing constant, which I will write down in a second. Again, I guess the normalizing constant is 1 over 2. Okay, so this state is actually the Kronecker product of B1 cross B2. So what happens if I measure the first qubit? Let's call it Q1, let's call it Q2, or let's use B1, B2, B1, B2. What happens if I measure B1? Well, with probability half, I get B1 equals 0. With probability half, I get B1 equals 1. But what happens to B2 when I measure B1? Well, B2, if B1 is 0, that's one of these two possibilities here. B1 is 0. Well, then B2 still remains. Again, I'll keep putting the normalizing constant whenever I can. Okay, because of this. When you fix B1 to 0, B2 still remains that. If B1 is 1, B2 becomes okay. So this is an interesting thing. So in this example, measuring B1 does not affect B2 and vice versa. On the other hand, in an entangled state, what you have is measuring one of the qubits collapses the other qubit as well. Now you can have states that are partially entangled. So for example, let's take an example here. Let's take the state which is a superposition of 0, 0, 0, 1, or 1, 1. Okay, and these are two qubits, Q1 and Q2. Okay, and the normalizing constant should be 1 by square root of 3. All right. Now, what's the idea here? So suppose I measure, let's measure Q2. Okay, I get two possibilities. It can either be a 0 state or it can be a 1 state. Okay, so with probability 1/3, it can be a 0 state. With probability 2/3, it can be a 1 state. Now, the interesting thing is, when Q2 measures down to 0, the only possibility that gets realized is the one that I have circled here, and therefore Q1 also collapses to 0. On the other hand, when Q2 collapses to 1, if that happens, then Q1 collapses to 0 plus 1, and don't forget the normalizing constant, square root of 2. Interestingly, if Q2 collapses to 0, Q1 completely collapses. If Q2 collapses to 1, Q1 partially collapses. So this is not like a full entanglement, it's like a partial entanglement, if you will. All right. So what is an what is the characterization of a non-entangled state? Well, a state is not entangled if you can write it as the Kronecker product of two qubits. So it's kind of to take two qubits and make them independent of each other. On the other hand, entangled states, the qubits are connected to each other. Okay, so measuring one affects the other. Okay, and this belongs to a very famous thought experiment by a trio of scientists: Einstein, you know very well, Podolsky, and Rosen. And this is called EPR paradox. Even though the paradox has kind of been resolved, I mean, depends on the philosophical underpinnings of quantum physics that you subscribe to, and so on and so forth. But the interesting thing about EPR paradox is what Einstein, Podolsky, and Rosen said is, let's take an atom that emits two photons in opposite direction, but stays in place. So stays in place. So what we know is that the speed of the photons are the same. The speed of the photons are the same. And if we know that this atom's position is at 0, 0, well, then what we know is that there are two photons that are moving around. Okay. And what I could do is, if I can measure the velocity here and thereby destroy the position, and if I can measure the position here and thereby destroy the velocity, I can completely characterize the state of both the photons, right? Now, what happens in reality is, if I measure the velocity of photon A or photon 1, the position of photon 2 also collapses. So in reality, whenever I measure something about one of these photons, the other photon also collapses. Okay, and because of this paradox, these kinds of states, entangled states, are also called EPR states. Okay, and this was the first time someone described the notion of quantum entanglement. The idea here is, if I measure some property of one of these photons, the properties of the other photon also collapses, and those photons can be really far apart. So the apparent paradox is something here is traveling faster than light, or information is traveling faster than light, which seems to be paradoxical, except that it doesn't work that way. What you have to imagine is, these two photons are part of the same system. They are kind of part of the same single entity until you do a measurement, in which case they split into two separate entities. Okay, and that's how you should think about it. And a quantum state, like entangled state, like 0, 0 plus 1, 1, behaves exactly the same way. It behaves exactly the same way. So these two states are entangled. The qubits are entangled. Okay, so entangled qubits are very, very interesting, and they are physically possible. Experiments have confirmed that such entangled qubits are always possible. And entanglement is one of the very important ideas in quantum mechanics. Without entanglement, it's not possible to do much. With entanglements, you really start doing interesting things in quantum algorithms. All right, we have looked at qubits. The question is, what can we do with qubits? All right. So the first thing you can do with qubits is you can always measure them. And we've already talked about the effect of measurement. So if you have alpha 1 S1 plus alpha n Sn, let's say they are normalized, then with probability modulus alpha 1 squared, this collapses to state S1. With probability, this collapses to state Sn. It collapses to state Si. So you know that a superposition like this is going to collapse to one of these states with some probability. Okay, and this is the measurement operator. And we can also do a measurement of, if you have k qubits, q1 through qk, and if your state is composed of k qubits, by the way, this bar with arrow is called the bra notation, and there's a dual of it which is called the ket notation. This is called the ket notation, and this is like row vectors and column vectors. Okay, I'm not going to worry too much about this. This is all quantum mechanics notation, and together you get what's called a quantum bracket. Anyway, let's not worry too much about it. The important thing is, if I have k qubits, then if I can measure one of the qubits at a time, I can measure all of them at a time. So I'm not going to go into detail of measurements. I already talked to you about what happens if I measure one of these qubits. I get some value, and then the remaining qubits either collapse or they remain in a quantum superposed state. All right, so these are important concepts. Hopefully that's clear. All right, now I can do quantum operations. So what are quantum operations? So I can take a single qubit, and let me look at single qubit quantum operations. Okay, so quantum operations are going to be a form of a linear transform. Okay, so if I send in a quantum state, let me call a quantum qubit alpha 1 times 0 plus alpha 2 times 1, then I get back a new quantum state. Okay, so I'm going to manipulate the probabilities of being 0 and being 1. And by the way, alpha 1 squared plus alpha 2 squared must be 1, and likewise alpha 1 hat squared plus alpha 2 hat squared must be 1. Okay, so immediately what this means is this must be the operator t cannot change the amplitude of the state. And all quantum operators are linear. So what does it mean to be linear? What it means to be linear is if I can specify t as 0 maps to, let's say, beta 1 0 plus beta 2 1, and 1 maps to let's call it gamma 1 0 plus gamma 2 1. So this is the how t operates on pure states. Okay, so if I input a pure state, then these are the outputs. So if I know how t operates on pure state, then on a mixed state alpha 1 0 plus alpha 2 1, the result is going to be alpha 1 times t of 0 plus alpha 2 times t of 1. Okay, so this is going to be alpha 1 beta 1 0 plus beta 2 plus alpha 2 times gamma 1 0 plus gamma 2 1. So the result is going to become alpha 1 beta 1 plus alpha 2 gamma 1 0 plus alpha 1 beta 2 plus alpha 2 gamma 2 1. Okay, and this can be seen, the action of t can be seen as applying a matrix. What is this matrix? So this matrix is going to become beta 1 gamma 1 beta 2 gamma 2, okay, to the values alpha 1 alpha 2. So this is going to be the matrix representation of a quantum operator. Okay, and because of quantum mechanics, quantum operators have to satisfy the following properties. They have to be reversible, which means that if I can apply a quantum operator to go from Q1 to Q2, okay, so if I can apply transform quantum state Q1 to transfer to quantum state Q2, then there is always an inverse operator by which I can go back from Q2 to Q1. Okay, so quantum computing is always reversible. Any quantum operation other than measurement is irreversible. Measurement is the only operator which you are allowing which is irreversible. You cannot reverse a measurement. Every other quantum operator from one qubit to another must be reversible, which means if your computation can go forward, you can also move it backward. All right, so that's a fundamental principle of quantum computing. All right, so quantum operators are linear, linear and reversible. Linear means that if I can tell you what the operator does to the pure states, okay, then that's enough. So if I can specify what the operator does to the pure states, and finally, they must be the third condition, which is slightly technical, is called unitary. So these operators must be unitary operators, which means that what T1 of 0 and T of 0 and T of 1 must be orthogonal. So T of 0 and T of 1 must be orthogonal. Okay, which means that if you take the dot product, they must equal 0. Okay, they must be perpendicular to each other. Let's not worry too much about it. Let me describe some possible quantum operators. The simplest quantum operator is quantum NOT. The idea here is the NOT gate. Okay, if you have a qubit Q, it inverts the qubit. So if it's 0, it inverts it to 1. If it's 1, then it inverts it to 0. So what's the matrix representation? The matrix representation is so 0, 1, 1, 0. Okay, so that's going to be the matrix representation. And I guess there must be like a minus here. Okay, so this is not quite correct. The real quantum NOT gate uses something called a Pauli spin matrix. Okay, so I'm kind of missing a negative sign somewhere, but don't worry about it. So hopefully we'll fix that later. But this is an example of a unitary operator. Okay, and it will take a quantum state. So for example, if the input state is 0 plus 1, let's say 0 by square root 3 plus twice 1 by square root 3. Okay, so this is going to be the state. Then this is going to be mapped to twice 0 by square root 3 plus 1 by square root 3. So this is an example of a NOT gate. It's a quantum NOT gate. Okay. Now what other quantum gates are possible? One very fundamental operation is called the Hadamard gate. Okay, the Hadamard. This is used all over the place. Hadamard gate. Okay, and slightly technical, this maps 0 to 0 plus 1 over square root 2, and this maps 1 to 1 by square root 2, 0 minus 1. This minus is important, otherwise they will need to be orthogonal. In terms of a matrix, this is going to look like this: 1 by square root 2, 1 by square root 2, 1 by square root 2, minus 1 by square root 2. Okay, so this is going to be the matrix. This is called the Hadamard matrix. All right. And interestingly, let's take an example. Let's take the state point. Suppose I take the state 1 by square root 2, 0 plus 1, and I apply the Hadamard gate to it. So this, when I apply the Hadamard gate to this qubit, the result is going to become 1 by square root 2 times 1 by square root 2, 0 plus 1 minus plus 1 by square root 2, 0 minus 1. And what you will see is this all cancels, the 1 cancels out, and you will get back the pure state 0. So interestingly, Hadamard gate on this state yields this state. And likewise, you can check that Hadamard gate on applied to this quantum is going to give you the pure state 1. Or if, for example, Hadamard gate applied to the pure state 0 gives you the uniform state. Okay, so Hadamard gate, so if you wanted to make up Hadamard gates, then this is kind of an interesting idea, right? So so we've looked at single qubit operations. So there are other examples. So one very important example is rotation by theta. So if you view the state as a vector, okay, you can rotate this vector, and you always look at counterclockwise rotations by an angle theta, okay, and this is called the rotation. The rotation matrix is cos theta, sine theta, minus sine theta, cos theta, and this is going to map I think this way, yeah, all right, and this is going to map 0 to 0 cos theta plus 1 sine theta, okay, so and then it's going to map 1 to minus sine theta 0 plus 1 cos theta. Okay, so this is a scalar, so it needs to be in front of it according to my notation. Sorry for the confusion. All right, so this is a rotation matrix by angle theta. All right, so there are some other interesting gates, okay, and you can also do operations on multiple qubits. Operations on multiple qubits. Now, if you have 2 qubits, you have 4 possible pure states. So your operations need to specify what to do with each of these 4 possible pure states. So your operation says what is going to happen to 0, 0, what is going to happen to 0, 1, what is going to happen to 1, 0, and what is going to happen to 1, 1. And you specify these, okay, and your overall matrix, so suppose you get 0, 0 is so you specify all this, okay. So your overall matrix for your quantum state is going to become like this: alpha 1, 1, alpha 2, 1, alpha 4, 1, alpha. So this column is going to become a row. So this is going to become the matrix representation of your quantum operation, and this needs to be a unitary 4x4 matrix. And again, I can define states like the gates like the Hadamard gate on 2 qubits. I can define things like the other kinds of gates on 2 qubits. I can define a rotation gate on 2 qubit. And so on. So if I wanted to write down 2 qubits, then it's a 4-dimensional vector. So I can only draw 3 dimensions. And then there's going to be a 4th dimension. Okay, and these are all 90 degrees. So I can't draw this on a piece of paper because this requires 4-dimensional drawing. Okay, but a 2-qubit quantum system gives me a 4-dimensional state space. And these are going to be 4x4 matrices, 4x4 matrices. Okay, let me mention a couple of other matrices that are useful. So I mentioned rotation. There is another important operation that you can also do, which is called the reflection. So you can take one axis or a bunch of axes or a bunch of vectors, and you can reflect a state around a vector. So you can reflect a quantum state around a vector, and that's an important operation. Okay, so you can view these as matrices, application of matrices to quantum states. You can also view this as geometric operations. Okay, and that is the very, very important fact about quantum qubits and operations on qubits. Okay, if this is clear, In the next lecture, I will talk about something very, very surprising that you can do with with entangled qubits that you cannot do with classical bits. Okay, I'll talk about that in the very next lecture on what's called Bell inequality. Okay, talk to you then. Bye. Okay, so in this lecture, we will look at the effect of entangled photons on a very interesting property called Bell's inequality. Okay, so let me explain what the idea is, and it's a rather fun game. All right, so let's say there are two players, Alice and Bob. Okay, and the two players, and then there's the central authority. Let's call them the person, the verifier. Okay, so Alice and Bob are initially sent to two different planets. Okay, so they are on Earth and let's say Mars or something like that. Why should we keep Alice on Earth? Let's send Alice somewhere else. Let's send Alice to, I don't know, Jupiter. And Mars, Bob is in Mars, and the verifier transmits, and they are not allowed to communicate, so they cannot communicate with each other. They are held incommunicado, and the verifier sends two bits. So he or she sends a bit B to Bob and bit A to Alice, and they are supposed to respond back with a bit, and let's call Alice's bit X and Bob's bit Y. Okay, and Alice and Bob win, and let's say they are allowed to return back to Earth if X XOR Y, and this is the XOR operator, equals A and B. What's XOR? XOR, if you remember, is the exclusive OR operator. It's basically, the truth table is like this. So far it's like the OR, except that 1 and 1 should give you a 0. So this is the only difference with an OR. It's called the exclusive OR operator. So if the two bits that I sent, A, and if I take the AND of the two bits, this is the AND, must be equal to the XOR of their response. So the AND of the two bits must be equal to XOR of response. And then Alice and Bob win. So if this is met, then Alice and Bob win. All right. Now, let's say each of these four bits, four combinations of A and B, so A and B, the bits that are sent to them, can be 0, 0, 0, 1, 1, 0, 1, 1, and each of these four are equally possible with 1/4 probability. With 1/4 probability, each of these four is equally possible. All right. Now, what happens? How do Alice and Bob respond? Okay. So the simplest strategy for Alice and Bob is to always respond with a 0. So simplest strategy is always respond with a 0. No matter what input they get, always say 0 and they are done. Okay. Now, if this is the strategy, then you can imagine what's going to happen. So in this case, A they are going to win. In this case, they are going to win. This case, they are going to win. But here, they are going to lose. So they are going to win with probability 3/4. So 3 out of 4 cases is going to be a win. All right. So this is 75%. And in fact, you can look at other strategies. So Alice can send back the bit she receives as is, and Bob sends back the negation of B. So the negation of B. So this could be another strategy, and you will find that again the winning probability is 3/4. And there are some bad strategies, like Alice always sends back a 0, and Bob always sends back a 1, and this is going to win just 1/4 of the time. Okay, so this is going to win just 1/4 of the time. Okay, so there is a very famous inequality, and this is called Bell's inequality, that no matter what strategy they use, the probability of winning by Alice and Bob is always less than or equal to 0.75. So no matter what strategy they use, the probability of winning is less than or equal to 0.75. But this is only assuming classical communication. Okay. Now suppose they were allowed to share some quantum. So this is under classical information. Now suppose they are allowed to share quantum information. What will happen is this bound will be broken. There is an easy strategy where their winning probability can be increased to something like 0.8. And what's the idea here? The idea is very simple. The idea is Alice and Bob, before they set out on their journey, they share an entangled qubit. So they share 2 qubits, Q1, Q2, and they share it in this state, which we have already seen before. And this is called the EPR state, the entangled state. So they share 2 entangled qubits. Okay, and then Alice takes the qubit Q1 to Jupiter. Well, she can't be on Jupiter. She's probably on Jupiter's orbit. All right, it's okay. And then Bob takes Q2 to Mars. Okay, and Alice has to keep Q1 and Q2 very carefully. They have to keep entangled qubits are very, very sensitive. They can lose their entanglement quite easily, but they take their entangled qubits and they keep it with them. Now, when verifier sends Alice and Bob their bits, okay, what Alice does is the following. If A equals 1, she makes a transformation. She applies a rotation of pi by 8. Okay, so pi being 180, pi by 8 is approximately 22.5 degrees. Well, not approximately, exactly 22.5 degrees. She rotates her qubit to 22.5 degrees. Likewise, if Bob gets the 1 bit, he rotates the qubit Q2 by minus 22.5 degrees, 22.5 in the opposite direction. But if Alice gets a 0, she doesn't do anything to the qubit. If Bob gets a 0, he doesn't do anything to his qubit. Now what they do is then they measure their qubits and send answer back. Whatever the result of the measurement is, they send answer back as X and Y. Okay. Now let's analyze this protocol, and since we know enough about all of these, let's analyze this protocol. And let me recall what measurement does, right? So measurement does the following. So if I have a qubit 0 and I rotate it by pi by 8, I will get cos pi by 8, whatever that number is, times 0 plus sine pi by 8 times 1. So I'm going to call this number C, and I'm going to call this number S. Okay, so whenever I write C, remember it's cosine pi by 8. Whenever I write S, it's sine pi by 8. And likewise, a 1 under a rotation of pi by 8 becomes minus plus cosine pi by 8 times 1. Okay, very good. All right, so now what happens? What happens is this. Let us imagine the situation. So let us say the bits that were sent to Alice was 0 and Bob got the bit 0. Okay, so what's going to happen is neither of them rotate their qubits. And therefore, Alice and Bob measure the quantum state 0, 0 plus 1, 1. Okay. Now what happens is Alice gets a 0, Bob gets a 0, and this happens with probability half. With other probability half, Alice and Bob both get a 1. Okay, now in either case, A and B is 0, and their response is going to be x equals y equals 0 or x equals y equals 1, but x XOR y is 0. So they will win for sure. There's no probabilities involved here. If Alice and Bob get a 0, they are going to win for sure. Now what happens if one of them gets a 1? Case 1, let's say Alice gets a 1, Bob gets a 0. If Alice gets a 1, Alice is going to take her qubit and rotate it. So the original quantum state was 0, 0 plus 1, 1 is going to be transformed under rotation pi by 8 of the first qubit. So just the first qubit gets rotated. That's going to become 1 by square root 2. This first 0 here, the first qubit here, becomes cosine pi by 8. So let me write it as C 0 plus S1 Kronecker product, this 0, plus minus S0 plus C1 Kronecker product 1. Okay, now I'm interested in them winning. So they will win only if, so A and B is 0. So they are going to win only if Alice and Bob send same bit back. So they both send 0 or they both send 1. So they both send 0 or they both send 1. And what's the probability of that happening? Probability of that happening is 1 by square root 2 c squared. Okay, sorry, half c squared. The square root 2 has to be, so half c squared plus half c squared. Why is that? Because remember, the probability associated with 0, 0 is c by square root 2. The probability associated with 1, 1 is c by square root 2. And if you want to add the two probabilities, so either 0, 0 must happen or 1, 1 must happen, well, probability is c squared, which is roughly 0.85. Okay, c being, remember, cosine of 22.5 degrees. All right, and this is case 1, this is case 2. Now case 3 is Alice got a 0, Bob got a 1. Okay, again A and B is 0. Now if you analyze this, you will get exactly the symmetric result to case 2, and the probability of winning is once again c squared, which is 0.85. Now the last case is more complicated. Both Alice and Bob get a 1. Since both Alice and Bob get a 1, A and B is 1. Okay, now what they are going to do is Alice is going to rotate her qubit by pi by 8, and Bob is going to rotate his qubit by minus pi by 8. So let C be cosine pi by 8, S be sine pi by 8, and then C hat, let's call it cosine of minus pi by 8. And if you know your trigonometry from high school, that's just C. S hat is sine of minus pi by 8, that's minus S. All right, hopefully this is correct and you remember this from before. All right, so what's going to happen? So the original qubit was 0, 0 plus 1, 1, and don't forget there's 1 by square root 2 here. Okay, now this gets transformed to the following: 1 by square root 2. So Alice is going to give her qubit a pi by 8 rotation. So this is going to become, Alice's qubit is going to become C0 plus S1, and Bob's qubit is going to become, this part is going to become C hat 0 plus S hat 1. Okay, and likewise, and this is the Kronecker product, plus here Alice's qubit is going to become minus S0 plus C1, and Bob's going to become minus S hat 0 plus C hat 1. Okay, and I won't simplify this. Let me just note that since A and B is 1, Alice and Bob are only going to win if X is not equal to Y. That's the only way when you get X XOR Y is 1, which is A and B. So to win, X must be 0, Y must be 1, or X must be 1, Y must be 0. So, okay, so what's the probability of ending up with a 0, 1? So with the 0, 1. All right, so 0, 1 probability must be, so you have a 0 and a 1, or you have a 0 and a 1. So that's going to be C S hat minus S C hat. Okay, so this is going to be times 0, 1. What about 1, 0? So probability of getting a 1, 0 is going to be, so it's going to be S C hat and then 1 C minus S hat, minus C S hat. Okay, now what's this? So this is nothing but C minus CS, because S hat is minus S, minus SC. Okay, so 0, 1. This is going to be CS plus CS 1, 0. So this is minus 2 cos pi by 4 sine pi by 4 0, 1, and this is 2 cos pi by 4 sine pi by 4 1, 0. Okay, and don't forget there's a 1 by square root 2. 1 by square root 2 everywhere. Okay, so in any case, this quantity is actually this is pi by 8, pi by 8, pi by 8, pi by 8. Okay, so 2 cos pi by 8 sine pi by 8 is nothing but sine pi by 4, which is 1 by square root 2. Okay, so this whole mess simplifies to minus 1 by 2, 0, 1, and this is going to simplify to plus 1 by 2, 1, 0. And by the way, you can simplify the other terms too. You get plus 1 by 2, 0, 0, minus 1 by 2, 1, 1. So this whole mess, after Alice and Bob apply their rotation, simplifies to this. Now Alice and Bob will win if these are the two possibilities that crop up, and these will crop up with probability half. So in this situation, Alice and Bob will win with probability half. So let's summarize. So in the first situation, which happens with probability 1/4, A and B are both 0, and the probability of win under this situation is 1. In the second situation, which happens with probability 1/2, here the probability of win is roughly 0.85, a little more than that. 1/4, probability of win is roughly 0.85, and with 1/4 probability, both of them get a 1. In this case, probability of a win is roughly 0.5, is equal to 0.5 actually. So now if I combine that, the overall probability of a win is 1/4 times 1 plus 2 times 1/4 times 0.85 because of these two, plus 1/4 times 0.5, which is 1/4 times 1 plus 2.7 plus 0.5, 1.7 plus 0.5, which is 3.2 by 4, which is 0.8. So already if they have two entangled bits, if I give them two entangled bits, they can beat the Bell's inequality. So quantum information can do more powerful things than classical information. All right, just by the virtue of sharing these entangled qubits, in fact, allows Alice and Bob to communicate, right? So they can communicate because of the nature of quantum bits. So in some sense, it's like Alice and Bob have two coins where if they toss it, the probability of turning up heads in both cases is correlated. Okay, so they have these quantum coins or correlated coins. So these are called quantum coins. So they have these quantum coins, which with they toss, the probability of both of them receiving heads or both of them receiving tails is nearly 1. Okay, and they can operate on these quantum coins and adjust this probability. All right. Now this is very interesting, and interestingly enough, this has been confirmed by experiments. This is not just a theoretical thing. This has actually been confirmed by experiments. And interestingly, entangled quantum information is fundamental to quantum cryptography. So it allows you to do things that are more interesting than classical crypto, and you get something called quantum crypto. And many quantum versions of crypto algorithms are what we expect to survive if, for example, factorization is proved to be polynomial time. If you can break RSA, then a lot of cipher systems that are based on the difficulty of the discrete log problem or the factorization problem can also be broken. And if that happens, then our backup is going to rely on quantum crypto. And there are many solutions for quantum crypto, things like quantum key exchange, that are being commercialized. So this is actually quite far along, much farther along than you imagine. People have taken entangled photons across Lake Geneva, for example, and this was already 10 years ago. In Switzerland, they had 2 entangled photons at each end of the lake, and they were able to come up with a secure quantum channel. Okay, things like that. All right, so this is illustrates one of the cool things that you can do with entangled bits. In the next lecture, I will talk briefly about a very clever algorithm for searching for a solution for a problem using a search algorithm called Grover search algorithm. I will briefly explain how that search algorithm works, okay, and give you a flavor of how quantum algorithms look like. All right, see you then. Bye. Okay, so now we will study an interesting algorithm, a quantum algorithm called the Grover search algorithm. Okay, it was proposed by quantum computer scientists called Grover. All right. Now, the interesting thing about Grover search algorithm is it can be used to solve a problem like SAT over n variables in time theta 2 to the power n over 2. Okay, and it's an interesting algorithm. It illustrates how quantum computing works and why quantum computing can achieve speedups. All right, and it's nice enough that I can explain to you based on everything we have learned so far about qubits and operations on qubits. All right, so let me set up the scene for the Grover search algorithm. What is it? Okay, so you're given a circuit, let's say a circuit made of AND gates, OR gates, NOT gates. So you're given some kind of a digital circuit over, let's say, n inputs, and you have an output. Okay, so let's call this a black box function f. All right, so you have an output, and I want to find an input to make the output 1. And this is just a classical circuit. All right, so this is just a classical circuit. All right, classical, what we will call a combinational circuit or a logic circuit. And if you think about it, this is equivalent to the SAT problem. All right, but it's kind of, it can accommodate other things too. So for example, you're given an array, let's say an array where element 1, element 2, element n, and some of these elements are zeros and some of these elements are 1. So which means that some of these elements are present and some of these elements are absent. Find an input I such that f of I equals 1. So this could be any arbitrary arbitrary black box function. All right. So the problem is, if you want to do in classical computation, the best known algorithm is 2 to the power n, and that's very simple. This algorithm is simply run through all possibilities, right? In the quantum algorithm, we are going to give you an algorithm that actually works in times square root of 2 to the power n, which is 2 to the power n over 2. So we are going to knock off a square root out of the algorithm in using the fundamental ideas in quantum computing. All right. Now let me give you a note about quantum algorithms. So quantum algorithm. So the input is going to be a black box function f implemented as a circuit, which takes in n-bit input and gives me 1-bit output. Okay. And this goes into the algorithm. Okay, and out comes, so here is the idea. So suppose fi we know secretly is 1, so I is the answer. Okay, so I being n-bit number is the answer. All right, so what the output is going to be is it's going to be I with high probability and something else, wrong output, an erroneous output, something else. Let's say 1 through I minus 1, I plus 1 through n, but this only happens with very low probability. So here is the fundamental thing. Quantum computation is fundamentally randomized. So any quantum algorithm is going to give you the wrong answer. It's going to give you the wrong answer some of the time with low probability, with very low probability, and the probability can be made. Let's say this probability is less than 1/4, and let's say this probability is greater than 3/4, right? So, but it gives you the right answer the majority of times. So if you keep running it, what you will find out is eventually in roughly like 2 or 3 steps, you will get the right answer. So the probability of repeatedly getting the wrong answer is negligibly small. Right? And that's the important thing. So you cannot repeatedly get the wrong answer. Eventually you will get the right answer. And how do you know if you get the right answer? Very simple. Feed it to the function f and check that it gives an output of 1. All right. So this is called, this is the nature of quantum algorithm. All right. Okay, so let me briefly summarize Grover's search algorithm. So what is the algorithm going to look like? So the algorithm is going to look like this. So what I'm going to do is, the first thing I'm going to do is take this function f with n-bit input, 1-bit output, and make it a quantum function, which means that instead of operating on classical bits, now this function needs to operate on qubits. But there is a problem. The problem is, if you take the classical gates like AND or OR, okay, these are not unitary function. These are not unitary linear maps. Okay, so in quantum computation, remember, you can only apply unitary maps, right? On the other hand, NOT works in quantum computing. So NOT gate works in quantum computing because you can always take the qubit 0, map it to the qubit 1. You can always take the qubit 1, map it to the qubit 0, and you can think of this as a unitary operation given by the matrix 0, 1, 1, 0. Okay, so this matrix gives you the required unitary operation. There might be a minus somewhere. I'm missing it. And an OR are not. And one of the main problems is they are not invertible, right? So you cannot write a function that goes from 2 bits to 1 bit. Such a function cannot be inverted, right? So if I have output of 0, I don't know which 2 inputs produced it. Is it 0, 1, or is it 1, 0, or is it 0, 0, right? So I do not know. So it's not invertible, and only invertible things can be done in quantum computation. But there is a trick, and using this trick, I can port AND gates and OR gates into quantum gates. How do I do it? So let us say an AND gate, a quantum version of AND gate, will have two inputs. Okay, so this is the first input, first qubit. This is the second qubit, and my goal is to do a quantum AND. It's just a classical AND, but it's a quantum version of the AND gate on these two inputs. What I do is I give myself a third qubit, and this is going to be the result qubit. I'm going to write the result in this qubit, and I'm going to set this qubit to 0. Okay, as a rule, all these result registers will be kept to 0. So the idea is very simple. So the unitary operation is going to map this whole thing back to, I'm going to recover Q1 and Q2. They are going to remain unchanged. And in the third bit, the 0 result bit, now I'm going to write the bit for Q1 and Q2. Okay, I'm going to take the AND of it. And this is fairly easy to see. This is going to be a unitary operation. So for example, I have 0, 0, 0 will map to 0, 0, 0. 0, 0, 0, 1, 0 will map to 0, 1, 0. 1, 0, 0 will map to 1, 0, 0. 1, 1, 0 will map to 1, 1, 1. And now this is the result bit, okay, which I have, by convention, it's always 0. Then these are Q1 and Q2. So this is one way of implementing AND. So the other four, so there are 4 more. So I have to specify what happens to 0, 0, 1, 0, 1, 1, 1, 0, 1, and 1, 1, 1. But these are garbage. Why is it garbage? Because they are violating my convention where I promise AND only if this bit is 0. Okay, and otherwise I just will not promise you anything. Okay, so this is a way of implementing a quantum version of AND, and likewise you can implement a quantum version of OR. Okay, and the nice idea is if you can implement AND, OR, and NOT, so then what you can do is you can implement any classical circuit, right? You can take any classical circuit F, okay, and you can make a quantum version of it. Now the only issue is the quantum version is going to take all the inputs of the classical inputs. Okay, so if there are n bits, and it's going to take some, you're going to have to prepare some number of bits k of fresh 0 bits to record the output, and then the final output will be, you will recover all the n bits. So all the n bits of the input are going to be unaffected, okay, because this is quantum computation. So all the n qubits are going to be unaffected. Okay, these are qubits, and then there's going to be the result qubits, the k of them are going to be some intermediate values, which we will ignore for now. And then finally there's going to be a result. Okay, so there is going to be a special result bit which is going to hold the result. Okay, so there's going to be a result qubit. So we have to prepare some qubits for holding intermediate values. So if you have a circuit like this, if you have an AND followed by an OR, let's say followed by a NOT gate, so you would prepare a quantum AND, and you would prepare like a fresh 0 qubit for this quantum AND. You would prepare a quantum OR, and you would prepare another fresh 0 qubit for this quantum OR. And by the way, this quantum AND is going to still output the 2 inputs, and it's going to have a result, intermediate result, which is this result 1, and then there is result 2, input 3, right? And then input 3 is also going to come out, and result 2 is going to come out, and then you can apply a quantum NOT, and this doesn't need a fresh bit because this is unitary, and then you have result 2. So now you have the 3 bits of input. They are going to come out unchanged, so the 3 qubits are going to come out unchanged, and your result is coming out in a register that you prepared with a 0 upfront. Alright, this is how you would implement a classical computing box in quantum. Alright, and here is the nice thing. So suppose I have a classical circuit F, okay, with n inputs, and I made a quantum version of it. And let's say the classical circuit had, to be more exact, let's say the classical circuit had 2 bits, B1, B2. Now the quantum has 2 qubits, Q1, Q2. Now suppose I prepared a quantum state 0, 0, 0, 1, 1, 0, 1, 1, okay, and then I prepared a special result register which is a 0, and I have the result register and the two Q1, Q2 unaffected, right? So the interesting thing is, if I take this Q1, Q2, take this qubit and pass it through the quantum version, it computes the value of f for all these 4 inputs simultaneously. So there is an interesting parallelism. So there is a parallel computation element in quantum computing where the circuit, the single circuit, is computing in parallel the result for all 4 configurations of Q1, Q2. And because I can do it in quantum operations, the output comes out, and I will get output like 0, 0, F0, 0, plus 0, 1, F0, 1, plus 1, 0, F1, 0, plus 1, 1, F11. So these are, F11 is the bit that corresponds to running F, okay? So you can do this, and this is where the magic of quantum computing, the parallelism of quantum computing comes up, all right? So what is Grover's search algorithm? So the first step of Grover's search algorithm is I'm given a classical box F with n inputs, 1 output. I'll make a quantum version of F, make a quantum version But remember, I need to, every time I do this, I need to prepare, every time I run F, I need to prepare a bunch of 0 intermediate result registers, okay? This is the important thing to run a quantum algorithm. If you want to run classical computations, you cannot do assignments. You cannot rewrite a qubit with another value. Just like you can do in a program, you cannot say x equals 2, x equals x plus 3. So this kind of assignment is not possible. You can't reassign in general unless this is a unitary operation, which is it. It isn't, right? So you can only do unitary operations, which is the big restriction in quantum computing. All right, so what is the next main idea behind Grover search? So let us assume that I have numbers from 0, 1, all the way up to 2 to the power n. Okay, so this is all the inputs are 0. Here, 2 to the power n minus 1, which is all the inputs are 1. And any number in middle. Okay, so let me write down, let us say f of I, secretly we know that f of I is 1. Okay, so I must be the answer. All right, so if you imagine this in a vector space, so what am I going to do is I'm going to initialize my something like this. So I'm going to initialize a vector u, which is going to be uniformly 0, 0, 0, 0, 0 plus 0, 0, 0, 0, 1 plus 1, 1, 1, 1, 1. So all n-bit numbers. How many of them are there? Well, there are 2 to the power n of them. And what's the normalizing constant? It's 1 by square root of 2 to the power n. Okay, let me call this vector u. And I'm going to informally write things like this. So I'm going to informally write it in 2 dimensions. So here is the special dimension I, and here is every other dimension. Because I will need, this is a 2 to the power n dimensional space. I'm just writing every other dimension, and let me call that E sub I. Okay, so this is going to be 0 plus 1 all the way plus up to I minus 1. I'm going to skip I plus 1 plus n minus 1, 2 to the power n minus 1. Okay, so this is going to be all the other dimensions, and I'm going to put it up like here, and with a suitable normalization constant. Okay, and u is going to look like this. So u is the vector, which is the uniform random vector, which is the sum of all n bits. So how do I get u? Interestingly, to get u, I'm just going to do the following. I'm going to prepare a quantum state 0, 0, 0, 0, 0. And interestingly, I'm going to apply the Hadamard gate to every bit. So I'm going to apply Hadamard gate is going to transform 0 to 0 plus 1, 1 by square root 2. So when I apply the Hadamard gate, I'm going to get 0 plus 1, Kronecker product 0 plus 1, Kronecker product 0 plus 1, and I'm going to do n such, or in this case I'm going to do n such Kronecker products, 1 by square root 2 to the power n, taking all the normalization constants out, and this gives me all possible n-bit numbers. So this gives me exactly u. All right, so this is how I prepare u. So u is going to be a very special vector in my space. Okay, and here is an angle between u and e sub I, and let me call this angle theta. So theta is the angle made between u and e sub I. I can actually calculate this angle. So what is this angle? So this angle is going to be the dot product of u and e sub I. Okay, so the dot product of u and e sub I is, and when I take the dot product, that gives me the cosine of the angle. Okay, and what is the dot product? I can calculate that. So u is basically 1 by square root 2 to the power n of this vector, all zeros plus the vector of all ones. Okay, and e sub I is very, very similar, except it's 1 by square root 2 to the power n minus 1. Okay, so just 1 less than that, of the vector 0, 0 all the way, except that the vector for I is missing. Okay, because ei is the vector of everything other than I. Let's see, everything other than I, which is secretly we know it's the result, but you know, this is not something we know. All right, so this is going to be the vector I plus 1 all the way up to the vector 1, 1, 1, 1, 1. Okay, now I is going to be missing, so I missing. So what's the dot product? Well, the dot product is just multiply term by term, so it's 1 by square root 2 to the power n, square root 2 to the power n minus 1 times, this is going to give me a 1 plus 1 plus 1 plus 1, and this is going to be 2 to the power n minus 1 of these. Okay, okay, so and when I simplify this, I get 2 to the power n minus 1 by square root 2 to the power n, square root 2 to the power n minus 1, and this is going to be square root of 2 to the power n minus 1 by square root 2 to the power n, and this is going to be square root 1 minus 1 by 2 to the power n. Okay, so when the dust settles, this is approximately 1 minus 1 by 2 to the power n by 2. Okay, okay, so this is cos theta, cosine theta. All right, now this is square root 1 minus, you know, cosine theta is 1 minus sine squared theta, and therefore sine squared theta is 1 by 2 to the power n, which is implies that sine theta is 1 by square root 2 to the power n, and since n is large, I can use something called a small angle approximation. Right, so in the small angle approximation, sine theta is approximately theta when theta is approximately 0, and therefore here theta will become 1 by square root 2 to the power n, which is approximately theta. Because n is large, this is going to be a small number. I can make this more formal. All right, so what is all of this in aid of? So here is the idea. My unknown vector I is going to be like this, and here is my vector ei of everything else, and here is my uniform vector u, and here is the angle theta. So what am I going to do? So I'm going to start with a vector w which is initially going to be u. Let me call this w at time 0 is going to be u. So w is going to initially coincide with u. At every step, what am I going to do? I'm going to use quantum operations to rotate w by angle 2 theta towards I. Even though I do not know I, I am going to rotate w towards I by 2 theta radians. How is that possible, right? How is that possible? And this is the amazing idea behind quantum algorithm, amazing trick behind the Grover search, right? This is where you get this amazing algorithm. This is why we study this. All right. So the idea is simply this. And why does this solve the problem? By the way, let us first understand why is this sufficient to solve the problem. So W0 starts like this. It coincides with U. Every time it makes a 2 theta progress. So what I do is I run it for roughly until this angle becomes coincident. So WK is going to coincide with this. So how many rotations do I need? So this is initially 90 degrees, so pi by 2. So I will need something like pi by 2 times 2 theta, which is roughly the number of iterations I need to run. And this is eventually theta is going to be 1 by 2 to the square root n. So which is going to be pi by 4 by 1 by square root 2 to the n, which is square root 2 to the n times pi by 4, which is theta square root 2 to the n. So in this many iterations, in k iterations, this vector w sub I or w sub j is going to coincide very closely with this vector I. And then I do a measurement. So here is the idea. So number 1, w sub 0 is going to be u. Okay, so prepare w sub 0. Number 2, for j equals 1 to k steps, where k is roughly going to be pi by 4 square root 2 to the n steps. Okay, so that many steps. Rotate w sub I plus I by 2 theta radians. And let's call this result w sub I plus 1 or j plus 1. This is the jth iteration. All right. And eventually measure w, return answer. Okay. And what we will show that what will happen is w sub 0 starts to be u, and every time if this angle is theta, it rotates by 2 theta towards the answer, which is going to be I. It's going to rotate by 2 theta every time. And after this many steps, it's going to be very, very close to I. So if I make a measurement, with very high probability, it will collapse to I, and with low probability, it will collapse to something else. So with very high probability, you will get the right answer. So all I have to convince you now is if I have a vector w, okay, if I have, and let's call this w sub j after j iterations. This is my answer I, but this is unknown. Okay, I don't know it. This angle is theta. This is the vector u, which is 0 plus 1 plus 2 to the power n minus 1. It's the uniform vector up to a normalization constant. This is going to be e sub I, which is everything but I. So I is not included. All right. So how do I do this rotation? So here is the idea. Let's call this angle alpha. Okay. So first step is I'm going to reflect wj about ej. So which means that I'm going to make a reflection, and it's going to give me this vector, and this vector is now going to make the same angle alpha plus theta but in the other direction. Okay, so now let's call this wj hat after reflection. Okay, number one. And number two is I'm going to reflect wj hat about u, this vector u, and when I reflect, now this angle is alpha plus 2 theta, so I get a new vector which makes an angle alpha plus 2 theta with u. So therefore this angle between wj plus 1 and wj must be 2 theta. So reflect about u yielding wj plus 1. So these are the two operations. So first operation is take wj and reflect about e sub I, and the second operation is take wj hat, the result, and reflect about u. Okay, so how do you do this reflection? So reflection is actually a unitary operation that you can do in quantum mechanics. Okay, so how do I do reflection? So what is reflection? So let me briefly explain to you what is reflection. So let's take a three-dimensional space example. Okay, so suppose I take a vector. Okay, let's take this vector 2, 3, 5. Okay, and I want to reflect this vector about the xy plane. So I want to reflect this vector about the xy plane. So how do I reflect it? Well, if I want to reflect about the xy plane, then x and y will become unchanged, and the only dimension is z, and z will flip. So the result of this reflection will become 2, 3, minus 5. So if I reflect around the xy plane, and by the way, if you write x as the qubit 0, if you write y as the qubit 1, if you write z as the qubit 2, then reflecting around the xy plane is reflecting around the qubit 0 plus 1. Okay, everything but 2. All right, which is simply going to take the dimension that you are not reflecting. So z is the dimension that I am not reflecting, and negate it. Okay, so this is what reflecting around something like a plane means. So what does it mean to reflect around E sub I? So remember, E sub I is 0 plus 1 plus up to I minus 1 plus I plus 1 all the way to n minus 1, which is going to be the orthogonal qubit to the qubit I, right? So what does it mean to reflect? So if you take a vector wj, you want to reflect. Let's say wj is alpha 1 times 0 plus alpha 2 times 1 plus alpha I times I. Okay, so let's say alpha 0, 0, alpha 1, 1, alpha I, alpha 2 to the power n minus 1 times 2 to the power n minus 1. So this must be 2 to the power n minus 1. What's the idea here? All these dimensions which are along your reflection plane will remain unchanged. The only dimension that will flip is alpha I, so which will become, so now you will get alpha 0 times 0 plus alpha 1 times 1, blah, 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 blah. The only thing that changes is minus alpha I times I, plus blah, 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 alpha 2 to the power n minus 1 times 2 to the power n minus 1. All right. So the only thing that changes is the alpha I coefficient. All right. But my problem is I do not know I. If I knew I, I'm done, right? But here's where the idea in quantum computing comes up. I have this box F. Okay. If I apply this box, this quantum F, the quantum version of F, let me apply the quantum version of F to 0, 0, 0 all the way to 1, 1, 1. So let me take the uniform state, and this has a name, we called it U. So let me apply the quantum version of F to U, or in this case, not to U, to this vector Wj. So let me apply the quantum version Now what is going to happen? So what's going to happen is you're going to have alpha 0, 0 plus alpha 2 to the power n minus 1, 2 to the power n minus 1. So this is going to be Wj, right? Now what's going to happen is you're going to get a result register, which I'm not showing. So you're going to get alpha 0, let's say 0 is this bit, and then you're going to get the result for it, let's say 0. plus alpha 1, and then you get the original qubit 1, and then the result for 1. Let's say that's also a 0. Okay, and let's say I is the only thing that's 1. So then you get plus blah blah blah. Now you get for alpha sub I, you get I. Okay, so let's say everything is 0. So this is f of 0. Let's say this is f of 1. Now for, let's say f of I is 1. So now you get f of I. Okay, and then everything else is going to be alpha 2 to the power n minus 1, 2 to the power n minus 1, but it's going to be a 0. Okay, so f of 2 to the power n minus 1. So you can always do this. Okay, so this is using the quantum f box. You get the value of f for various qubits. Now the only thing that's going to become a 1 is I. So let me do the following. Let me take a new unitary operation where if I have a bunch of qubits and then I have the result. If the result is 0, I am going to keep it unchanged. On the other hand, if the result bit is 1, I'm going to flip and negate it. I'm going to just negate this operation. Okay, so the idea here is based on this last bit, I'm going to either add a minus sign or not. So if you apply that kind of a, and that's going to be a unitary operation. Okay, if you apply that operation to this qubit, what you would get is alpha 0, 0, and then the result qubit is going to be 0. Okay, result. These are going to be the inputs. Plus, the only thing that flips is alpha sub I, and that's going to be flipping to 1. Okay, because this result is a 1, it flips, and then alpha 2 to the power n minus 1, and then 2 to the power n minus 1, and then a 0. All right, so this is a very, very clever trick where because I have this box F, I am able to carry out this reflection. So this reflection is carried out by this box F, and this is also the power of quantum computing. This box F operates in parallel over all possible inputs at the same time. So operates in parallel. Okay, so this is how I compute a reflection around E sub I. All right. Now the next idea is, once I have reflected my vector, so this is W sub j, this is E sub I, and I did this reflection. Let's call this W sub j hat. The next step is reflect around U. So reflect around this U vector, and remember U vector is 1 by square root 2 to the n, all zeros plus all ones. It's the uniform vector. Now, what's the idea here? The idea here is if I want to reflect around U, so reflection around U, is the same as first apply a change of basis. So first apply change of basis to move the vector U to simply the vector of all zeros. Second, reflect about the vector of all zeros. And third, change of basis back. And this is called a conjugation. So you change of basis back, where you now change the vector basis from 0, 0, 0 to back to U. Okay. Now this change of basis has a name. This is simply the Hadamard operator. This reflection is very, very easy. Just take the coefficient that corresponds to this qubit and keep it, and flip every other qubit. Just negate every other qubit. All right. And this change of basis back is also the Hadamard gate. So interestingly enough, I've just managed to convince you that the two basic operations inside the for loop can be done using quantum operations. So what are the two basic operations? Remember, this is W sub j. The first operation is reflect around E sub I. And then the second operation is reflect around U. and you get w sub j plus 1, and you can prove very simply that the angle between w sub j and w sub j plus 1 is 2 theta, and this is going to be in the direction of this unknown, but the result I. So if you do roughly theta 2 to the power square root 2 to the power n ops of this, you are going to get very close to the result, and then you do a measurement. And the measurement is going to, with a very high probability, yield the result, and with lower probability it might yield the wrong answer. I can quantify what this probability will be, but I will spare you the mathematical details. So this is very interesting. So Grover's search, instead of taking theta 2 to the power n to search on an n bit, it now reduces it to theta square root 2 to the n. Unfortunately, this doesn't mean that I have solved an NP-complete problem, right? So I have still not solved an NP-complete problem. So let me conclude this lecture on quantum algorithms by talking a little bit about the most important quantum algorithm so far to date, which is Shor's algorithm for factoring RSA numbers. So given a number n, which is the product of two prime factors p and q, you can in polynomial time find the factors. But the catch is on a quantum computer. So this is why we are so interested in quantum computer, because efficient quantum computer means that RSA is broken. So an efficient quantum computer can break RSA, and because you can break RSA, internet security as we know it is broken. Okay, and this is why quantum computers are so interesting and so important, that we do not know of a good classical algorithm for breaking RSA. All right. Now the interesting thing is the factoring algorithm, even though it's not known to be in P, it's not known to be NP complete either. So it's not known that you. So the big open questions are, big open question: where does the power of quantum computing really lie? So we have all polynomial time problems on a classical computer, and if it can be solved in polynomial time on a classical computer, you should now be more or less convinced that you can solve it in polynomial time on a quantum computer. And you have NP, and we do not know that there are problems in this donut hole. This donut hole might be empty, but there are some NP complete problems. Now the question is, the big $1 million open question is, are there NP complete problems that are efficiently on a quantum computer? Okay, and that is a very important and literally $1 million question. Okay, and hopefully, if you're interested, I can give you lots of pointers to books that discuss this subject much more. Lots of pointers to the complexity theory. So there is a class called BQP, which is the class of all algorithms that can be solved in polynomial time on a quantum computer, and its relationship between classical randomized algorithms and polynomial time algorithms is an open problem. All right, so there is plenty of open questions in quantum computing, and there is a few very exciting algorithms for problems which we cannot solve easily in classical computing. Hopefully this gives you an idea of the flavor of quantum computing, of quantum algorithms, and I hope this was an interesting lecture for you. And if you are listening to this for the summer of 2018, this concludes the entire class on algorithms. This was a really fun class for me to teach. I totally enjoyed teaching this class. I hope it was fun and educative for you as much as it was for me. So all the best for your future endeavors. I really hope you enjoy learning more about computer science and more about algorithms in general. Feel free to contact me if you want pointers to learn more. Okay, all the best. Bye.